Hi, everybody. Dr. L here, and in this quick segment, we're going to take a look at a crash course in a few different types of algorithms. Full disclosure, a lot of these algorithms can be used for both classification and regression type problems where the output is also continuous, but we're going to frame the discussion today more in the context specifically of classification problems. So first thing we're going to take a look at today is something known as a support vector machine. We're going to look at a hard margin case where we have a very nice separable data set, and we'll consider soft margin where we allow some observations to violate the boundary of the classification boundary. And we'll talk about the role of nonlinear transformations. We've mentioned this in the context of regression in prior segments, but this is an important point that applies much more broadly than to just support vector machines. But in general, we'll also take a very quick look at neural networks. We're not going to do anything too technical, but just to kind of get an idea of the general structure of how they work and the features of the backpropagation algorithm for how to solve it, which is really predicated on gradient descent framework. And we're going to look at a classification and regression tree, and really more importantly, an application of CART, which is the random forest prediction technique, which utilizes essentially a forest of regression trees coupled with some resampling and a majority voting procedure to decide on a given classification for a particular data point. We'll wrap up by discussing some unsupervised learning techniques related to clustering. We'll talk about the difference between k-means and x-means clustering. Under x-means, you don't have to decide how many clusters to use. The computer figures that out for you. As well as hierarchical clustering. And there's two types of hierarchical clustering. We'll take a look graphically, at least one of those. And then in the next video segment, I'll show you guys how to implement an SVM. We'll implement CART, and we'll implement random forests in R. You can also implement neural networks, but I will leave that for a future segment because those are a little bit more involved, as you will see. So moving right along, let's talk about support vector machines. These are a fairly powerful model, powerful technique based on implementing something that is known as a separating hyperplane in order to partition our input space into different classification regions. And this technique specifically uses a quadratic programming implementation in order to estimate the beta parameters or the weights. We use a quadratic programming. Hopefully you remember quadratic means we have things squared, so it's a very specific type of programming structure. And the question we're going to think about when we think of structuring a support vector machine, at least in terms of classification problems, that's what we're going to look at today, but this could be used to predict a continuous variable as well. That is for another time. But the question we want to think about in terms of classification is what is the best hyperplane we can draw to separate the data into its classes based off of the sample data that we have. And of course, we want to make sure we generalize well. So let me show you here an example of what a separating hyperplane is. If we had a bunch of data points, we got some blue ones that are positive, we got some red ones that are in the negative class. All right, so we have these two features, x1 and x2 along the x-axis, x-axes, and our y variable here is an output variable, either 0 or 1, right? It's a particular class. And it could be continuous, but we're breaking that into a classification region here by trying to put this separating hyperplane in between the pluses and the minuses. All right, so we have some data here. We got some plus observations below. We got some data up here that are minus observations in the region above. And we want to know what is the best way for us to draw this plane that separates the data. We don't want it too close to the red threshold, or else some actual red points might violate it. We don't want it too close to the blue threshold. So how do we do this? Okay, and that's exactly the problem that we need to solve in constructing a support vector machine. That is what it does, is it draws the best hyperplane to separate your data. Now, we could have a nonlinear support vector machine using a nonlinear transformation going to Z space, which I'll talk about a little bit later. And that means this hyperplane could actually be a curved manifold and not a plane at all. It could be a nonlinear hyperdimensional manifold that we're trying to construct here. So fairly complex and a very powerful algorithm for classification and continuous prediction as well. And ideally, our data allows us to just draw a flat plane through it. Right? Let's consider the case of data that is known as linearly separable. If the data is linearly separable, and here we're looking downwards into the x1, x2 plane, we have these two features here, x1 and x2, along the horizontal and vertical axes. Question is, how do we divide that region up in order to separate that data? Okay, and you'll notice we can do that here. We can draw a line right here. That's one particular hypothesis that separates the data. But you'll notice there are really an infinite set of possible hypotheses. Here is a different hypothesis that separates the data. So which is better? Is it the first one? Is it the second one? Or are there other ones that are better? We need to think about what is the criteria that makes one hypothesis better than another. So that's really the question at hand here, is how do we draw the best separating hyperplane? Okay, so here are three pictures that I borrowed from a colleague at Caltech. Several of these diagrams are full disclosure. And as we move from the left diagram to the right, you'll notice the data points are the same, but the way we draw the boundary is a little bit different, right? In that first diagram, the boundary is really close to that bottom left data point, right? It's extremely close to this data point. Okay, and out of sample, there may be other red dots that could fall on the other side of that boundary. So the boundary line here that we're referring to, the hyperplane that we're referring to specifically, is the middle of what looks like that yellow highway strip. Okay, that is the separating hyperplane. So I got these magenta arrows pointing to that separating hyperplane in each of those three diagrams. And the question is, which one is the best? Okay, and I want to make the argument that the one farthest to the right is actually the best one. It's farthest enough away from the red points, or even if there's a little bit of error on new data points, we'll probably capture them, right? So the red region here, we are saying, we're defining as everything kind of up and to the left. Okay, that would be the red classification region, everything there, and everything down and to the right would be the blue region below that separating hyperplane. And you'll notice we've given ourselves a little bit of error margin. Right? We have some distance here, some error margin on either side of that hyperplane that divides that region into two. Okay, and the way we're going to really formalize the problem here is we're going to think about, well, let's draw a hyperplane in this space where we get the fattest margin, where we get the widest possible highway in this picture. Okay, that means we're going to be far enough away from those data points where we can be confident we're reasonably separating them from each other into their respective classes. So that is really the goal. Okay, the support vector machine, what that does is it chooses the optimal hyperplane by finding the set of hyperplanes that can separate the data, and then essentially choosing from that set, from that hypothesis set, the hyperplane that induces the widest possible margin. Okay. I do have a few slides here on the mathematics of the programming formulation, so feel free to pause the video and take a harder look at those. But I mentioned before, this is a quadratic programming algorithm. Here are how our betas show up in the objective function, beta transpose beta. That's the sum of the square betas, right? So we're minimizing some quadratic function. This is a constrained optimization problem. And if you're familiar with the constrained optimization framework, oh, by the way, this B here is really our B0, beta 0. Okay, so I took that out of the beta vector. That's actually a choice variable in the problem here that we're going to look at. And the question is, how do we solve this problem? Well, you're going to get the computer to really do the heavy lifting. And note, it is specified as a minimization problem. So we can think of this as like our cost function, and we're trying to minimize it in order to maximize the margin, right? So Those two problems are equivalent. Maximizing the margin is the same thing as solving this particular minimization problem that we're looking at here in this diagram. If you're familiar with the Lagrangian technique, you can write out the Lagrangian here using a Lagrange multiplier for the constraints. Okay, and the Lagrange multiplier are these alpha values. So we're showing you in the slide here the associated first order conditions for the gradient vector, as well as the first order condition here associated with that, that B term, B0 term. There are also first order conditions associated with the alpha parameter that just gives you back the constraint set. But again, if this is more detailed than you're interested in, you can, if you pause the video here, take a look at this later. Solving this problem generates also what's known as a dual problem. It's another problem that shares the same solution properties. And if you were to solve the first order conditions of the problem on the previous slide, in terms of the alpha parameters, in terms of those Lagrange multipliers, then you can actually rewrite the dual problem as a maximization problem. Okay, where we're maximizing with respect to these alpha parameters. And this gives you kind of an alternative perspective. This is really the one that applies in practice here. You recover the alphas by solving the following problem here. In terms of the alphas, exploiting duality. And again, we can rewrite it as a min problem and think of this again specifically in the context of some sort of cost minimization framework. So this information here, a little bit technical. If you want to take a harder look at it, please do. I will probably follow up with more segments sometime in the distant future on this. But for now, all you need to be aware of is that this utilizes a quadratic programming technique. And we're trying to maximize the margin by drawing that hyperplane through the data. And the solution to the problem that does this for us, okay, allows us to recover the betas through the set of first order conditions. And these betas depend specifically on values of our inputs or observations known as support vectors. So let me show you what the support vectors are graphically in this problem. You'll notice there are some observations that do not define the boundary region drawn here, right? These observations circled in green do not at all define the boundary of the margin that is drawn. But we have a few observations that do define the boundary, right? This observation defines the boundary, this observation defines the boundary, this observation defines the boundary. Those observations that I just circled in pink there, magenta, they are what we call support vectors. Those are observations or vectors in our input space that define the boundary of the optimal hyperplane, right? That is maximizing the margin here. Okay, so we can get the betas to the first order condition, and we can use those to solve for that remaining intercept B value through the constraint sets here. But again, not super critical that you know those details at this point. Just that what we're doing is we're trying to put in that hyperplane to classify the data by maximizing the margin between those two potential classes from our training data. And you might say, oh, this is all well and good, but probably in reality, we're going to be dealing with cases where our data is not linearly separable. There's no way I can draw a line through this diagram on the left, right? If it's a straight line, in a way that leaves me with zero in-sample error, right? I'm going to wind up getting some in-sample error. However, we could think about using a nonlinear boundary on the same data. And if you compare these two things, you'll notice in the left-hand diagram, right, we have some in-sample error. Right? En is bigger than 0. Why do I say that? Well, it looks like we have an observation over here that's misclassified. Right? We're classifying as blue as positive, but it's actually a negative, and we have an observation over here that's misclassified. So we have some in-sample error. I would argue, though, conversely, in the right diagram, our in-sample error is 0. We've drawn that hypothesis to perfectly capture or fit our data in terms of this classification problem. Now, hopefully remembering about generalization and that, well, the more complex model isn't necessarily great for generalizing out of sample, and that still applies here. So you should still be thinking in that same vein of thought. So the question is here, what do we do if we run into this situation where the data is not linearly separable? And the answer to that question is, well, we can do one of two things. We can try to find some nonlinear transform that allows us to draw these curved boundary regions like in the right picture here. Or we can accept some positive amount of in-sample error. We can allow some observations to violate the boundary that we've set, and that is known as softening the margin. Okay, if you have a hard margin, your EN is 0. You are perfectly characterizing the data. But if you have a soft margin, you'll maybe allow some data points to violate the margin. You won't have a perfect in-sample error, but that may generalize better out of sample, right? There's a trade-off there we ought to be considerate of. So what do we do? Well, if it's not linearly separable, it could fall really into one of the following categories. Okay, not linearly separable, or not separable, period, given the constraints on the hypothesis set. And in order to deal with the two cases below, we would do the following. In the case where it's not linearly separable, we would check, well, is there some nonlinear transformation we can use? Logging the data, squaring things, polynomial power transformations we could use, where we could transform the data into a new space where the problem does look linear, and I'll show you a picture of that in a moment. Or we could use something called a soft margin. And we will start off today looking at option 1 here, using nonlinear transformation. So let's take a look at the data in this next example. Okay, hopefully you can convince yourself that this data is definitely not linearly separable. Okay, there's no straight line hypothesis you could draw through there that would break that region up in a way where our in-sample error for this classification problem would be 0. Okay, so we're going to do the following. Okay, I'm going to argue that if we transform the data by doing something with each coordinate here. So note we have here our two axes. Okay, we really have x1 along that axis. And we can think about having x2 along the vertical axis here, with two different features. And note that our axes are actually centered at -1, -1. Hopefully you see that here, that we've shifted the axes over a little bit. So the origin is not actually down here. The origin in this particular diagram is smack in the middle of the picture. 0, 0 is right here at the orange dot, right in the middle. That is the origin here. So all these points that are to the left of the origin and below the origin, if they're to the left and down, right, down in this region here, okay, that is the negative orthon, or the negative quadrant. And what we're going to think about doing here, what I'm going to suggest is that if we took the coordinate points of each data point, all of those red data points and all those blue data points, if I took the coordinates and I squared them, I will argue that that will change these data points in a way that makes the problem linearly separable when we look at the problem from the perspective of the square of these data points. So if you look, for example, at the observations down here in the very bottom right, let me clear this up. But if you look at these observations down here in the very bottom left, okay, they have negative x values and negative y values. Well, what happens when I square the x coordinates and the x1 coordinate and the x2 coordinate? Well, they're going to become positive, which means those data points are going to move from this quadrant up here into this quadrant. They're going to become data points with positive x1 and x2 coordinates. After we square them, the transformed coordinates will be positive. Okay, how about these guys? Well, these two data points down here have negative x2 coordinates. Okay, so when we square them, their x1 coordinates will still stay positive, but the x2 coordinates, which are negative, will become positive, and they will move these points also up here. Okay, last but not least, we have these data points over here, which have negative x1 coordinates, but positive x2 coordinates. So when we square those data points, we square both coordinates. That's going to make the negative x1 coordinate positive and move these data points again over here. And the blue data points, they will move a little bit as well. Okay, but I'm going to argue they're all grouped tightly around the origin, so they're not going to move as much. So that is what we're going to consider here. We're going to use the following transformation. Let's create a new variable. Instead of x1 and x2, let's consider them z1 and z2. We'll rewrite the problem in z space, where we're going to define the z variable as just the x variable squared. So we're going to take each coordinate, x1 and x2, and we're going to square them. That is our phi transformation here. We're going to transform the data. And when we do that, I want you to take a very close look at what happens. As I suggested, the red data points all move to the top right. Okay, and now note, after we've transformed the data, I do not have x1 and x2 anymore on the axes. Okay, what are we looking at on the axes? Well, we now have z1 and z2. And note in this diagram, the origin is at the bottom left corner here. And we are now looking at the problem in what I'm calling z space. We got z1 and z2 instead of x1 and x2. What is z1? Z1 is just x1 squared, and z2 is just x2 squared. But now we're thinking about the problem in a different space. And notice once we've transformed that problem, now it is linearly separable. Now we can separate. And once we separate it, we classify them. And if we have to get back the original x data, we can recognize here, hey, in order to go from x to z, we squared everything. So if I wanted to go backwards, right, if I wanted to run that transformation backwards, then we just take the square root of the z's to get the x values back. So this process that we're looking at here in terms of using a nonlinear transformation, it's pretty cool. We started with data that was non-separable in the top left diagram up here. And then we use our transformation to make it separable. So that's z space in the top right panel. Then we went ahead and implemented our optimal hypothesis in the z space. And then we can take the inverse of our transformation to bring us back to the original x space where we can do our prediction. Okay, so that is the idea here. And an important lesson, and this applies not just to support vector machines, but in general, sometimes using that z-space transformation, that nonlinear transformation, can be useful, even for other problems besides this data separability problem. Okay, this lesson applies to most classification models in general with respect to the role that nonlinear transforms play. Okay, sometimes the problem is easy to solve after transforming it, but it was not easy to solve in the original form. So in the specific case of the SVM, okay, you can also reformulate that quadratic programming problem fairly easily here, where the z values show up instead of the x's. So it's pretty easy to run that transformation. It doesn't make the math that much more complicated. So again, if you're interested in that, take a look at the programming formulation details there. The other way we could get around the case of separability is by allowing some data points to violate the margin. And in order to implement what we call a soft margin support vector machine, okay, we're going to utilize something known as a slack variable, where a slack variable will show up in the optimization problem in a way that allows us to violate an inequality for a particular observation. Okay, it's essentially what that does in the programming formulation. We introduce the slack variable. It allows us to violate the boundary inequality for a certain observation or for multiple observations. And depending on the size of that slack variable, we can have larger violations or smaller tolerable violations here. But that will allow us to generate an SVM boundary. Okay, it could be linear or nonlinear if you use that Z transform, but it will not have a perfect in-sample prediction error. It will have a few observations that do violate the boundary. So to wrap up the discussion of SVM here, okay, to conclude, okay, support vectors, when we transform them, okay, they live in that Z space. But in the X space, we can get them back by writing that transformation backwards. But we can think about the margin really being maintained in either space. Okay, so whether or not this is Z space or X space, okay, we see here we have our support vectors. Okay, they are there. And the support vectors are really the ones that define the optimal parameters. Remember, I think in an earlier slide, I had the betas were equal to the sum of the alphas times the support vectors. The support vectors determine the model complexity here. So this generalization result here, very important for SVMs. Your out-of-sample error is bounded on average by the number of support vectors divided by n minus 1. Okay, so the more support vectors you have, the more complex the hypothesis is, the more potentially curves there are in the boundary of the margin that you are generating. All right, so point is, the more support vectors there are, okay, the higher that out-of-sample error is going to be on average. You don't get as great of a generalization due to higher complexity. But if you have a model with fewer support vectors, that is a simpler SVM. So the number of support vectors determine the complexity of the SVM model. Okay, so that is it for our discussion of support vector machines. We will pick up with neural networks and the remainder in the next segment. Hope you enjoyed, and we'll see you soon.